You're welcome to our channel, Physics Calculation Center. For your regular update on physics calculation past questions and present questions, please visit our channel, press the subscribe button and the notification button so that we can be up to date with our calculations. Thank you very much. Now, this afternoon, we have questions here so that we can apply our knowledge of linear expansivity. In our last video, we can apply it in our calculation. Now, let's see question 1. It says, steel bars each of length 3 meters at 29 degrees centigrade are to be used for constructing a rail line. If the linear expansivity of steel is 1.0 times 10 to the minus 5 Kelvin per Kelvin, calculate the safety gap that must be left between successful bars if the highest temperature expected is 41 degrees centigrade. Okay, so the question says we should calculate the safety gap. So to calculate the safety gap, what we do is safety gap is found by calculating change in length, because gap has to do with length also, change in length. Don't forget the formula. The formula says linear expansivity equals change in length over length before expansion, temperature after expansion, minus temperature before expansion. Okay, so, and it says change in length. So we'll just do change in length. It becomes, so we can cross multiply this to give us this L1 theta 2 minus theta 1 equals delta L. Okay, so delta L, which is the change in length, now becomes delta L becomes linear expansivity, which is 1.0 times 10 to the power minus 5. Okay. Then the change in temperature, 41 minus 29. When you do this, it gives you 0.0 L1, the original length before expansion. Don't let us forget that. 3. Okay, so that is 0.0003 times 12, which will give us 3.6 times 10 to the power minus 4. Okay, meters. So this is the safety gap needed, because it says the safety gap that must be left. So the safety gap, because what this one is saying is, basically you know that it's talking engineering. So the steel bars, because steel bars, there has to be ways to do engineering. In engineering, there are things we do. We test materials, and we need to understand how materials behave. Metallurgy engineering. So this material needs quality space. So we need to calculate it to know what would happen. Is that okay? So that is the gap that is left between successful bars if the highest temperature. So that is the projection. For you to rise to this temperature, this is the gap that we have to leave. So it gives you 3.6 times 10 to the power minus 4, or 0.0 or 0.0036 meters. Anyone? Okay. Example 2. A bridge made of steel is 600 meters long. What is the daily variation in its length if the night time and daytime temperature are 10 degrees centigrade and 35 degrees centigrade respectively? The linear expansivity of steel. This is, the first question is WAEC 1989. The second one is JAM 1992. So let's look at that quickly. Okay, let's look at that quickly. Daily variation is same thing as daily variation. Solution 2. Daily variation is same thing as change in length. Yes, it's the same is the same as increase or change in length. Okay, good. So having said that, so let's bring out our parameters now. A bridge made of steel, so that means length before expansion is 600 meters. Okay. Temperature after expansion is 35 degrees centigrade. Temperature before expansion is what? Before expansion is 10 degrees centigrade. And the linear expansivity of steel in this case is 1.2, 1, 2, 3, 4, 5 times 10 to the power minus 5 Celsius. Okay, so using which we know, that is delta L over L1 theta 2 minus theta 1. Okay, so change in length evidently becomes delta L equals linear expansivity theta 2 minus theta 1. Okay, we have the linear expansivity, we have the length before expansion, and we have the temperature before expansion and after expansion. 35 minus 10. So this will give us 1.2 times 10 to the power minus 5 times 600 times 25. If you do this one on your calculator, it will give you 18 centimeters. So what this one means, if you look at this in centimeters, because this one is in Celsius, this is in meters, this one is in Kelvin, this one is in Kelvin. Yes, so you can understand, when you're working in centimeter, there's the centigrade, but if you're working, that's Kelvin. So this is 18 centimeters. So this is the daily variation that happens here to the bridge. Variation, daily increase that happens. And I hope we understand this calculation. And in our next video, when you ponder on this properly and you look through it, in our next video, we do more calculations to drive home our point. I'll see you there. Thank you.